October 3rd, 2025. That date had been marked boldly by astronomers for ages. The moment 7 probes circling Mars would aim their lenses at the solar system's most enigmatic newcomer in recent memory. These included 2 from NASA, 2 from the European Space Agency, 1 from China, and 1 from the United Arab Emirates. Each one ideally placed to snag the sharpest snapshots yet of an object from beyond our system. Just the Hera instrument on NASA's Mars Reconnaissance Orbiter was set to deliver clarity down to 30 kilometers per pixel, 20 times crisper than Hubble's best efforts. This was supposed to be when we unlocked secrets about 3 Atlas. But it turned into the start of an eerie quiet. 2 days prior to the close approach, on October 1st, the U.S. government came to a halt. NASA's site blinked out with a basic notice. The agency is suspended because of expired federal budget support. Then, 4 days after, when the European Space Agency shared their shots, it was merely a blurry pale speck drifting amid the stars. A single photo from 7 probes. What happened to the other pictures? Exactly what did those lenses capture as 3 Atlas zipped by Mars at a distance of 30 million kilometers? And after all the build-up, why does it seem like somebody yanked the shades down just before the main act? Before we plunge into what could be among the oddest concealments in contemporary stargazing history, do me a solid. Smash that like button and hit subscribe if you haven't. Then chime in below. Where are you tuning in from? What's the local time? And do you reckon NASA's hush is just red tape or something way more intentional? If you're up for boosting our crew, pass this clip along on X, Facebook, Reddit, or your chat apps. Appreciate you sticking with us. Chapter 1. The Ideal Arrangement. Let me rewind you to July 1st, 2025. The Atlas scope in Rio, Chile, spots a speedy intruder slicing through the outer reaches of our solar system. In no time, skywatchers dig up earlier shots from storage. These came from various Atlas setups globally and the Zwicky Transient Facility at Palomar Observatory. The intruder had actually been snapped as early as June 14th, though no one clocked it then. Once they chart its path, one detail jumps right out. This isn't circling the sun, it's barreling straight through. Dubbed 3 Atlas eventually, it marked the 3rd verified interstellar visitor following Oumuamua in 2017 and Borisov in 2019. Yet unlike its predecessors, 3 Atlas showed up with a bonus, a route that felt way too neatly arranged to be pure luck. Picture the ecliptic plane of our solar system, that thin disk holding all the planetary orbits. Incoming interstellar stuff usually hits from odd directions. Oumuamua entered at 123 degrees to the ecliptic, Borisov at 44 degrees. But 3 Atlas? A mere 5 degrees off, spot on with the plane housing our worlds. Avi Loeb from Harvard crunched the stats. The odds of an interstellar arrival hugging within 5 degrees of the ecliptic by sheer coincidence? About 0.2%, 1 in 500. Now layer on more. 3 Atlas would skim past Mars at 30 million kilometers on October 3rd, graze Venus, and head toward Jupiter in March 2026. The joint chance of an interstellar body threading by 3 big planets, in order on random whim? 0.005%, 5 in 100,000. It's no wonder certain experts started side-eyeing it. Wild comets rarely arrive primed for primetime views. But the path was only the opener. As the summer wore on and additional scopes zeroed in on 3 Atlas, fresh data piled up. The Hubble Space Telescope grabbed pics in late July, with the object 277 million miles from our planet. Those visuals upended the norm. Typical comets, in photos, display a vivid core trailed by a streamer fleeing the sun's pull. Sunlight and winds shove the dust and vapors rearward, forming that iconic tail everyone knows. 3 Atlas flipped the script. Hubble revealed a radiance, sure, but it projected ahead sunward, not trailing back. The haze of diffused light reached out in front, as if the thing were slicing into resistance instead of getting shoved along. And trailing it, where a bold tail should loom, zilch, just a vague hint of stuff that didn't sharpen until late August. David Jewett at UCLA worked over those Hubble frames. He gauged the leading shine spanning a few arcseconds. Converting that angle at such range to real dimensions, the luminous area spanned thousands of kilometers. What really gave experts pause, though? The stretch was about 10 times its width, forming a stretched droplet form aimed at the sun. Comet cores venting naturally usually yield rounder, balanced outflows. Especially intriguing is the way solar radiation pressure ought to be shoving the material rearward. On August 6th, the James Webb Space Telescope examined 3 Atlas via its near-infrared spectrograph. This instrument dissects the makeup of celestial bodies by scrutinizing the precise light wavelengths they release or soak up. The discovery from Webb stood out as peculiar. The gaseous envelope encircling 3I Atlas consisted mainly of carbon dioxide, accounting for 87% of the mass. Carbon monoxide constituted roughly 9%. Meanwhile, water, which dominates in the vast majority of comets we've examined, only represented 4%. Consider all the comets detected by humans within our solar system. They generally consist of water-laden icy chunks that originated in the frigid outer zones of the sun's primordial disk. As they draw near the sun and heat up, the water ice turns directly into vapor, forming those striking tails linked to comets. Yet 3 Atlas appears constructed in a markedly different fashion. A 87% carbon dioxide content is virtually unprecedented. Just one other comet in our archives exhibits a comparable pattern. That's Comet C2016-R2, spotted by Pan-STARRS, which likewise revealed an exceptionally elevated carbon dioxide to water proportion. Between August 7th and 15th, the savoring Space Observatory, NASA's spectrophotometer dedicated to the history of the universe epoch of reionization and ICE's Explorer, monitored 3I Atlas. savoring functions in the infrared spectrum, focusing especially on wavelengths near 1 micrometer, allowing it to gauge object sizes through the sunlight they bounce back. The information gathered by savoring pointed to an even more astonishing revelation. From the volume of infrared light reflected by 3I Atlas, the core might measure up to 46 kilometers across. That's 46 kilometers. To put it in perspective, 2I Borisov, the prior interstellar comet, featured a core pegged at about 1 kilometer. If savoring's readings prove accurate, 3I Atlas would dwarf it by a factor of 1,000,000 in mass. 1,000,000 times, indeed. Allo shared his breakdown of the implications behind this size gap. He figured that at a solid density, should 3I Atlas truly reach that scale, the bare minimum mass comes to 33 billion tons. And that's merely his conservative figure. The body might actually be far bigger. He highlighted an issue that renders the stats even more alarming. Assuming interstellar objects adhere to a standard size spread, we ought to have spotted hundreds or thousands of tinier ones prior to stumbling upon an entity this enormous. The Atlas telescope system has surveyed the heavens for 10 years now. Across that span, only 3 interstellar intruders have shown up, and the latest one is abruptly 1,000,000-fold bulkier than the one before. Such a pattern defies the expected probability trends. That is, unless the size assessments are off base. Unless savoring picked up not the core proper, but a vast dust shroud enveloping a far tinier heart, which raises its own headaches. Should 3I Atlas possess a thick dust halo expansive enough to echo that much infrared glow, then where is the tail? Solar radiation pressure would drive all that dust aft, yielding a dazzling trail evident in any photo. Yet Hubble and fellow scopes observed chiefly forward scattered light with scant trailing debris. During August and September, Earthbound facilities gathered further insights. On August 25th, the Very Large Telescope in Chile conducted spectral analysis of 3 Atlas. It picked up cyanide CN molecules venting from the body at around 20 G/s, with 3I Atlas positioned 285 astronomical units from the Sun. What drew notice, though, was the swift escalation in that output as the comet neared the Sun. The cyanide output grew in line with heliocentric distance to the exponent of 9. For such a sharp correlation is extraordinarily rare. Typical comets exhibit output rates that follow distance to the power of -2 to -4, a value of 9. For borders on the impossible, the VLT findings uncovered another oddity. They spotted nickel within the vapor jet near 3 Atlas, yet no iron. Nickel absent iron. In the natural world, these elements virtually always co-occur, stemming from supernova blasts and embedding into nascent solar systems at set proportions. Detecting nickel sans iron resembles spotting smoke minus flame. It arises in niche industrial settings involving nickel alloys, but for pristine cosmic entities, it's downright bizarre. Early in September, hobbyist sky photographers Michael Jagger and Gerald Raymond snapped shots of 3I Atlas amid a full lunar eclipse. Their image revealed an unanticipated sight. The comet, previously deemed reddish across all spectral surveys, now shown green. Green-hued comets aren't rare. The tint usually arises from diatomic carbon molecule C2, which fluoresce green under solar ultraviolet stimulation. But the catch lies here. Prior spectral work by Luis Salazar Manzano's group at the University of Michigan indicated that 3 Atlas suffered from severe carbon chain scarcity. The comet displayed notably reduced amounts of C2 in this comet. 3I/Atlas boasts more C3 molecules than any previously documented icy body. Yet if it shows no signs of diatomic carbon, what accounts for that eerie green hue? A leading theory points to the sharp rise in cyanide output spotted by the VT instrument. Under specific circumstances, cyanide can emit greenish light, though the underlying reactions still don't fully align. Consider the mix: elevated carbon dioxide levels, scant water vapor, diminished carbon chains, plentiful cyanide, nickel present but iron absent, and a puzzling green luminescence that defies expectations from its chemical makeup. All this suggests an entity that strays from every known model of ordinary comets. By the end of September, 3I/Atlas had drawn near enough to the Sun that Earth observers faced real challenges. Its position aligned too closely with the Sun in our view, overwhelming it with intense sunlight. Ground telescopes on Earth essentially lost track of 3I/Atlas amid the dazzle. That's when Mars stepped in as a key vantage point. Though farther from Earth than our Moon, Mars in early October 2025 aligned in its path to offer orbiting probes a superior perspective on 3I/Atlas. As our planet's direct view faded, Mars is sharpened. 7 probes orbited the red planet, fitted with imaging and spectral tools originally tuned for its terrain but adaptable for unique tasks. NASA's Mars Reconnaissance Orbiter housed the HiRISE camera, the high-resolution imaging science experiment, widely regarded as the sharpest lens dispatched to any world beyond ours. From its Mars perch, HiRISE discerns details as fine as 30 centimeters, aimed at 3I/Atlas during perihelion. Its precision equated to roughly 30 kilometers per pixel. This marked a 20-fold improvement over Hubble's July snapshots of the intruder. NASA's MAVEN probe, the Mars Atmosphere and Volatile Evolution mission, featured an imaging ultraviolet spectrograph to probe 3I/Atlas's UV emissions and chart gas patterns in its envelope. The European Space Agency's Mars Express carried a high-resolution stereo camera, plus Omega and Spicum spectrometers for breaking down its makeup. ESA's ExoMars Trace Gas Orbiter included the color and stereo surface imaging system, CASIS, alongside the NOMAD spectrometer and a mid-infrared sensor. China's Tianwen-1 orbiter supplied its moderate-resolution imaging camera. The UAE's HOPE mission added the Emirates Exploration Imager, plus EMIRS and EMIT spectrometers. These 7 craft, with their array of lenses and analyzers, stood poised to gather intel as 3I/Atlas swung nearest to Mars on October 3rd. Scientists across the globe expected this to yield the sharpest insights into the cosmic newcomer so far. The setup was ideal. The schedule aligned flawlessly. The gear was primed. But just 2 days prior, the U.S. federal government initiated a shutdown. Chapter 2. The Silence Protocol in a Government Shutdown. Select agencies halt while others run minimal staffs for vital functions. NASA usually sends home about 80% of its staff during such crises. Communications teams shut down. Online presence fades. The primary site shows the usual notice on expired budgets. Core missions, however, press on. Mars satellites keep circling. Sensors stay active. Information streams from probes to antennas, gets logged and archived. The shift hits public sharing hardest. Under routine conditions, NASA's unprocessed images from Mars operations refresh nonstop. Take the Perseverance rover. It beams shots from its cameras to open servers for public perusal. Normally, these unrefined files pop up mere hours after capture, often quicker, thanks to heavy automation, refining them into polished, vetted, shareable products demand skilled hands, though. Experts must review the feeds, fix device flaws, merge shots when useful, and craft notes for wider audiences. On October 1st, 2025, that expertise vanished from duty. More than 15,000 NASA personnel got layoff alerts. Thus, as 3i/Atlas hit its Mars flyby on October 3rd, the specialists who typically handle and distribute probe visuals were sidelined at home, barred from work tasks. The European Space Agency, insulated from U.S. budget woes, ran full tilt. Its Mars Express and ExoMars Trace Gas Orbiter both targeted 3i/Atlas as scheduled from October 1st through 7. The probes swiveled their optics toward the outsider. ExoMars's TGO snapped a sequence of 5-second shots with Cassis. Mars Express tried for views via its high-resolution stereo camera, but the 0.5-second exposures fell short in detecting such a faint, far-off object proved challenging. For days after the comet's close approach to Mars on October 7th, the European Space Agency made the Cassis photos available to the public. Researchers and astronomy fans, who had eagerly awaited this moment, now had material to study. The visuals depicted a blurry pale speck gliding through a backdrop of stars. The surrounding stars showed up as trails since Cassis had followed the comet's motion throughout the exposure period. The comet 3I Atlas itself looked like a somewhat stretched patch, intense at its core and fading toward the borders. These shots verified that 3I Atlas was real and had zipped past Mars right on schedule, yet they offered scant insights into its makeup or form. Nick Thomas, the lead scientist for the Cassis tool, described the difficulty involved. The device was built to image Mars's vivid terrain from distances ranging from hundreds to thousands of kilometers. Aiming it at a weakly lit body some 30 million kilometers away stretched the hardware far outside its normal specs. The comet came across as about 10,000 to 100,000 times dimmer than standard subjects. That Cassis picked up any signal at all highlighted its remarkable adaptability, though the clarity suffered as a result. A Vibe scrutinized the Cassis visuals closely. He observed that the luminous halo encircling 3I Atlas in the shots spanned roughly double the size of the reference stars in the identical views. Accounting for Cassis's angular precision, this equated to around 680 kilometers across for the observable coma. That was about 10 times narrower than Hubble's earlier sightings. Still, Hubble benefited from extended exposures and a bigger mirror. Cassis managed to pick out just the most luminous heart of the object, overlooking the dimmer outskirts that stretched out further. One intriguing point a Vibe highlighted was how the spread of diffused light near 3I Atlas visually echoed what Hubble had recorded in July, only squeezed into a tighter footprint because of the tool's constraints. The findings indicated no significant surge in gas release had happened in the months since. For a standard comet nearing the Sun, one might anticipate a sharp rise in activity from stronger solar warmth. The steady look suggested either that the body wasn't reacting to sunlight like ordinary comets or that its changes were far less obvious than anticipated. At the same time, curiosity about NASA's footage grew stronger. 7 probes were on hand. The Mars Reconnaissance Orbiter's high-rise instrument ought to have delivered incredibly sharp depictions. MAVEN's UV spectrometer was set to chart the spread of gases. However, no such material surfaced in open databases. The Perseverance rover's automatic unprocessed image streams kept flowing, displaying routine rocks from Jezero crater, but no refined views of 3I Atlas emerged officially. The day after the encounter, on October 4th, an item in the Perseverance raw image collection drew notice. The right-hand navigation camera, a NAV cam mainly for ground driving, had snapped a photo at 21:33 Mars local time. It captured a stretched band of brightness against the night sky. The timing lined up with 3I Atlas's expected position from Mars. Hobby stargazers quickly grabbed and pored over the file. Simeon Schmaus, a space imaging specialist who often tweaks mission data from public sources, combined several NAV cam shots to enhance subtle features. He spotted what looked like a hazy glow in the Corona Borealis area, matching predictions for 3I Atlas's spot. Stephen Burns assembled a 9-minute sequence from back-to-back NAV cam frames, illustrating a vivid form traversing the sky over Mars. Yet the shape of that trail sparked debate. In the combined NAV cam view, the item stretched about 4 times its breadth, giving a tube-like or elongated profile. Online discussions exploded with parallels. One user likened it to the planet-devouring cylinder from the 1960s Star Trek's Doomsday Machine tale. Some drew links to Oumuamua, which also showed a stretched form. Although Oumuamua's ratio hit about 10:1 from its brightness shifts. Did 3i Atlas truly have a cylindrical build, or was some other factor causing the look? A Vibe tackled this in a thorough breakdown. He figured the NAV cam shot was probably a merged set of hundreds of single exposures spanning about 10 minutes. In that span, 3i Atlas would have shifted noticeably across the Martian view. Mars circles the Sun at 24 kilometers per second. 3i Atlas sped along at 67 kilometers per second against the Sun in a backward path opposite Mars's. That speed difference between the comet and planet worked out to a track of about 50,000 kilometers across a 10 during the brief integration window. Amateur stargazers who combined multiple frames without adjusting for the object's movement would end up with a trail. The extent of that trail would hinge on the total duration of the combined exposures, rather than the true size of 3i/Atlas. Individual captures from the navcam, limited to a maximum shutter speed of 3.28 seconds, would depict 3i/Atlas as a simple roundish blob. When those are merged, it fosters a false sense of stretching. Imagine snapping a picture of a vehicle speeding along a road in the dark with an extended shutter. The vehicle could be small and boxy, yet it shows up as an extended glow in the shot. That glow reflects only the path it took while the camera was open, not its real form. A parallel dynamic is at play in this case. The tube-like look in those hobbyist-edited photos probably stems from movement smearing, instead of 3i/Atlas actually being stretched out. Even so, NASA offered no verification on whether the navcam shots captured 3i/Atlas at all. The organization stayed quiet. The spotlight image for that week on the Mars Reconnaissance Orbiter section of NASA's site, covering September 28th to October 4th, featured a navcam shot from Perseverance, yet without any caption pinpointing the glowing item. With the federal budget impasse and public relations team on leave, such reticence might make sense, though the vagueness fueled endless conjecture. Soon after, unconfirmed buzz rippled through astronomy hobbyist circles claiming NASA had shared initial updates with chosen major news sources on October 4th, merely a day post-encounter. Those sessions supposedly framed 3i/Atlas as a routine comet, sidestepping the odd traits that had baffled experts. No backup data or analyses followed. No visuals emerged, just spoken guarantees of ordinariness. Dr. Michael Sulla, operator of the Exopolitics site and a longtime investigator of official hush-ups in space matters, highlighted a recurring trend. He linked it back to a pair of insiders who spoke out in 2001. Donna Hare, employed as a graphics specialist for NASA's partner Philco Ford, and Carl Wolf, a U.S. Air Force Staff Sergeant holding top-secret encrypted access, both shared accounts at the Disclosure Project media event led by Dr. Stephen Greer. Hare detailed her role at the Lunar Receiving Lab in Johnson Space Center, where her clearance let her access restricted zones. She recounted observing NASA image specialists digitally erasing oddities from moon photos prior to distribution. She consulted several internal sources who verified it as routine practice. Wolf recounted his duties at Langley Air Force Base, handling gear for analyzing photos from the lunar orbiter projects. He asserted he'd viewed proof of man-made forms on the moon's hidden side, material deemed sensitive and excised from released editions. Regardless of one's view on those statements, they set the stage for what Sulla terms scrubbing, the deliberate excision of contentious details from cosmic visuals before they go public. The method has developed gradually. In the initial phases of Mars probes, satellites streamed real-time signals that hobbyist listeners on specific bands could pick up. When curiosities surfaced in those streams, alerts raced through radio enthusiast networks. NASA's fix involved dropping live transmissions in favor of postponed drops with embedded editing windows. The International Space Station has periodically aired unfiltered views of our planet via outer cams. Over time, audiences have flagged sightings in those streams that resist simple answers. Peculiar glows, formed objects tracing bizarre routes. Each time something like that pops up, the broadcast jumps to a solid color or pivots to another view. NASA usually chalks it up to transmission glitches or standard angle shifts, but the moments align too neatly with the spotted oddity. Mars operations mirrored this shift. Initial outings pushed out photos swiftly, sometimes in mere hours. Yet as curiosity spiked and scrutiny software advanced, NASA added review tiers. Now, shots undergo adjustments for accuracy, glitch fixes, assessments, and narrative vetting prior to unveiling. This upholds valid research needs. Unprocessed probe info can be cluttered, riddled with device flaws, or misconstrued absent background, but it also inserts a delay for spotting and managing tricky visuals. Dr. Michael Sulla suggested that the ongoing scenario why this pattern holds true for 3I/Atlas as well. A total of 7 probes snapped photos of the intruder. Several of them, especially the Mars Reconnaissance Orbiter equipped with its advanced high-resolution lens, surely grabbed sharp, intricate shots. Yet those pictures are nowhere to be found in official archives, despite ongoing automated data streams from various sensors, implying that officials chose deliberately what to share and what to keep under wraps. Let's review the timeline. On October 1st, the federal government shutdown kicks off. By October 3rd, 3I/Atlas swings nearest to Mars. Then on October 7th, the European Space Agency drops some blurry snapshots from its instruments. Days pass, October 8th, 9th, 10th, 11th, 12th, and NASA stays mum. Nothing in the way of refined visuals, engineering analyses, or research articles dissecting the Mars encounter info. Total quiet on the airwaves. Avi weighed in on the matter in an NBC News chat. He tackled head-on the idea that the shutdown was a plot to obscure details on 3I/Atlas. True to form, his reply came with right attachment. The lag, he noted, doesn't point to signs of alien smarts. Rather, it's a hallmark of earthly bungling. He got the irritation but pinned the hush on red tape messes over any planned cover-up. That might well be the case. Maybe the quiet stems purely from laid-off staff and jammed-up operations. Still, the coincidence in timing stands out. Following weeks of build-up, with several probes lined up ideally, and the astronomy world zeroing in on October 3rd for solid insights into this odd newcomer, the lights went out right when the performance was set to begin. And this coincidence, deliberate or not, echoes a broader legacy of secrecy in cosmic explorations. Folks crave openness. Researchers hunger for the raw info. Yet agency sluggishness, security rules, and data handling chains form logjams where details enter but fail to exit, often not soon, and occasionally never. Chapter 3. Concealed by the Sun. The date of October 29, 2025, looms large, signaling perihelion, the spot where 3I/Atlas dips to its minimal solar distance. That's 1.36 astronomical units, about 203 million kilometers, situating the comet slightly inward from Mars's path. From our planet's vantage, this setup poses a visibility challenge. 3I/Atlas will sit nearly straight behind the Sun in our line of sight, lost in the blinding solar glow, utterly invisible to Earth-mounted scopes. The occlusion lasts from late October clear through much of November. Ground observers forfeit sight of the interstellar guest right when its behavior should peak. As bodies near perihelion, solar warmth ramps up sharply. Comets usually hit maximum venting at this stage, their frozen materials turning straight to vapor under fierce sunlight. Should 3I/Atlas prove a genuine comet, this closest approach ought to spark dazzling outbursts, vivid streams of vapor and particles, and possibly even splitting if heat overwhelms the core's hold. But ground watchers can't witness the spectacle. Our sun's disk seals off the panorama. Such events happen often enough. Comets routinely duck solar ward, and experts just bide time until they reappear opposite. What sets this apart is the web of mysteries already enshrouding 3I/Atlas. The odd makeup, the bizarre path, the vanished Mars pass visuals, all stack up to leave the entity vanishing from scrutiny at a pivotal juncture. Avi highlighted the stakes in an October blog entry. For a true comet like 3I/Atlas, perihelion could lead to disintegration. Heat pressures and the sun's pull can rip apart delicate frozen forms. Remember comet Shoemaker-Levy 9, which splintered nearing Jupiter in 1992, shredded by gravitational tugs before chunks slammed into the planet. Plenty of comets have crumbled inbound to the sun, buckling under the blaze. Uneven gas bursts can also rev up a comet's spin, mimicking small engines to twist the core if venting patches unevenly. Such speeding rotation adds outward pulls. Take Comet 32P/Iya Makami, which came undone in 2016, probably from frantic whirling sparked by lopsided emissions. Should 3I/Atlas shatter at perihelion, skywatchers might spot several fragments popping out in early December rather than a single intact form. Yet Avi sketched another possibility too. If 3I/Atlas turns out artificial, if it's a probe instead of a wild comet, this solar hideaway offers a prime window. Shielded from Earth's gaze by the sun, it might adjust course unseen. It could harness the sun's pull for a slingshot boost. Reshaping its path could be adjusted actively, unlike a mere inert stone. It might deploy tiny vessels or subprobes that detach from the core structure and settle into varied paths around the sun. The backward-moving course plays a key role in this setup. 3I Atlas travels counter to the way planets circle the sun. In the perspective of the object itself, worlds seem to close in on it instead of drifting away. Such positioning eases the math for rendezvous maneuvers. A subprobe ejected from 3I Atlas with some speed directed against the primary's velocity could decelerate compared to the sun, shifting to a stable loop orbit instead of hurtling off on an unbound hyperbolic path. These subprobes might then linger, stationed on routes that would cross paths with Earth, Venus, or Mars as those bodies keep their solar loops. Imagine scattering trail markers on a well-trodden path through the woods. There's no need to target each marker precisely at a hiker. Just position them where the route is sure to pass. The reverse path of 3I Atlas ensures its launched subprobes would cross planetary tracks organically by dialing back their solar speed. The exact moments of interception would hinge on the timing and spots of deployment, yet the layout inherently supports future meetings. This idea implies purpose, advanced engineering, and skills that push the limits of what most experts deem plausible. Yet Lowe has always embraced probing slim chance ideas if they align with the evidence at hand. He scores 3I Atlas a 6 on his Loeb scale, where 0 means purely natural and 10 means clearly artificial. A 6 points to real doubt. Plenty of oddities to merit deep analysis, but insufficient proof for firm judgments. Michael Sulla delved deeper into these notions via his exopolitics outlet, outlining 11 potential models for interpreting 3I Atlas. These span from straightforward natural causes, like a big comet with quirky makeup, to tech-driven ideas, alien scouting device, derelict intergenerational vessel, intentional outreach vehicle, or aggressive armament platform. Sulla avoids picking favorites, instead contending that official science too quickly shuts down options without full scrutiny. Among Sulla's more captivating ideas is the white hat theory. In this view, 3I Atlas embodies a joint venture between benevolent alien groups and progressive factions in Earth's defense and spy networks. The entity is said to emit signal frequencies, vibrational signatures that shape awareness and hasten enlightened growth. Its appearance, Sulla claims, aligns with rising transparency pushes as more insiders step up and public knowledge of hidden initiatives expands. This sort of theorizing clearly steps outside conventional scholarly talk. It blends UFO lore, mind exploration, world affairs, and outlier science into a tale that scholars would largely reject. Still, Sulla has built a following over years by chronicling secrecy trends in government, logging insider accounts, and crafting systems to link scattered weird events. Debate rages on whether these systems truly capture the world or just overlay fancy connections on scattered noise. One thing's certain, voids in released details breed wild guesses. When NASA skips out on promised photos, when offices hush up amid key viewing periods, when shared data stays sealed, folks inevitably weave stories to plug the holes. The closest solar approach adds fuel to this pattern. From late October to mid-November, ground telescopes on Earth can't spot 3I Atlas. It hides in a viewing gap, shielded by 200 million kilometers of sun's glowing matter. Orbiting scopes at alternate spots could hold a clear view, though their focus priorities and info-sharing timelines limit that. ESA's probe to Jupiter's frozen satellites, the JUICE craft, sits ideally placed. JUICE took off in April 2023 and is heading to Jupiter through a winding route with several gravity boosts. Come November 2025, JUICE will be situated to glimpse 3I Atlas from afar, right after the object's solar skim, when it might show peak vigor. From November 2nd to 25th, JUICE will study 3I Atlas with multiple tools. The Janus imaging array will snag visible light shots. The main spectrometer will chart makeup across visual and near-infrared bands. The UVS ultraviolet instrument will probe gas outflows. The PET particle instrument is designed to detect how solar wind interacts with the comet's gas emissions. By employing a variety of tools, this setup promises to deliver detailed insights into the dynamics of 3I/Atlas at its peak activity. However, complications arise. The JUICE probe is functioning in a setup with limited communication options. Positioned near the Sun as seen from Earth, it uses its primary antenna to block heat, forcing reliance on a secondary one that sends information at reduced speeds. Moreover, JUICE is on the opposite side of the Sun from our planet, requiring signals to travel an extended route across the solar system. Together, these issues ensure that readings from the November flyby won't arrive on Earth for several months. According to the European Space Agency, information from the 3I/Atlas encounter won't be ready for review until February 2026, 3 months post-event, leaving scientists and enthusiasts in the dark about the perihelion happenings for that entire stretch. 3I/Atlas will reappear from the Sun's shadow in early December, observable once more via ground telescopes. Yet the key perihelion window stays shrouded until the JUICE transmission lands. Adding to this is NASA's Juno probe, which has been circling Jupiter since its arrival in July 2016, probing the planet's weather patterns, magnetic influences, and gravity field. The project has seen repeated extensions, with activities slated to persist at least until September 2025. Conceptually, Juno might catch sight of 3I/Atlas as it nears Jupiter's neighborhood in March 2026. That said, NASA has powered down Juno's imaging systems. The JunoCam, a color camera mainly for engaging the public, got turned off in September 2025, mere weeks prior to when 3I/Atlas would come into view. Officials pointed to energy limitations and the priority of essential science gear. JunoCam was viewed as an extra feature outside the main goals. Deactivating it to save power for critical components aligns with practical operations. Still, the schedule feels off to certain watchers. Juno had the potential to snap up-close photos of 3I/Atlas during its Jupiter approach, yielding views no other mission could match. Yet the imagers fall silent exactly when the chance presents itself. Accident or arrangement. Your take might vary based on trust in official openness. What's clear is that 3I/Atlas hits a string of blind spots right at its most compelling moment. Terrestrial scopes go blind in late October. Juno's optics are dormant. JUICE gathers intel but holds it back until February. Mars-based craft, which might have offered sharp snaps in early October, stay quiet. Their findings withheld or perhaps classified. The outcome? A prolonged silence spanning weeks, during which this enigmatic interstellar guest moves unchecked. Should 3I/Atlas act just like 2I/Borisov at its 2019 closest solar pass, showing standard comet traits, breaking apart organically, or holding together on its curved path without veering? Then the doubts will look exaggerated looking back. Yet if 3I/Atlas pulls off something unforeseen, like steering, deploying payloads, or altering its course in non-natural ways beyond emissions or pulls from gravity, the truth will only surface afterward. And without steady monitoring, sorting natural events from possible intentional ones proves incredibly tough. This haze affects Earthwatchers too. Hobbyists with scopes of 8-inch aperture or bigger ought to detect 3I/Atlas once it clears the sun's brightness in early December. At an expected magnitude of 10, it's accessible to dedicated backyard setups. Groups of enthusiasts will surely aim their gear upward, keen to snapshots after the extended quiet. But their views will capture the consequences, not the action live. A breakup at perihelion? They'll spot scattered fragments. Intact survival? One body to follow. Any steering? The path might stray from forecasts. Piecing together the precise sequence from the hidden interval demands guesswork, trajectory math, and side-by-side checks against earlier sightings. No post-event breakdown can fully bridge that observational void. This loops back to accountability for organizations. When entities like NASA hold tools beyond the grasp of individuals or even many universities, they turn into gatekeepers. Guardians of data play a crucial role. When they share findings swiftly and in full detail, scientists and the general audience can assess the proof together. However, if they hold back releases, limit entry, or offer only partial details, they generate imbalances in knowledge that breed doubt. Chapter 4. The Mass Dilemma. Time to circle back to an issue that warrants deeper scrutiny than it first gets. Estimates of 3I/Atlas's dimensions fluctuate dramatically based on the tool employed and the method applied, turning the effort to align them into a real conundrum. This goes beyond mere scholarly tallying. The object's mass profoundly influences all our conclusions about its composition. Consider the initial sightings from Earth-bound observatories. Upon first spotting 3I/Atlas in July, researchers gauged its luminosity and applied conventional notions of albedo to gauge its scale. Assuming a reflectivity of 0.05, common for comet cores, one can reverse engineer the reflected light to figure out the required extent. Those preliminary figures pointed to a width of about 10 to 20 kilometers. Next came Hubble's view of 3I/Atlas on July 21st. The photos revealed a hazy radiance spanning a few arc seconds. Yet pinning down the true core's dimensions amid that haze was challenging. The gaseous and dusty envelopes around comets, known as comas, often dwarf the rocky heart. Hubble's clarity constrained how accurately experts could delineate the edge between core and envelope. Come August 20th, following further scans, Hubble's results indicated the core's width ranged from 440 m up to 5.6 kilometers. That's a ceiling of 5.6 kilometers, so the real measure might lie anywhere within. At the upper bound, 5.6 kilometers stands out, but keep spherex in mind. Those mid-August infrared readings hinted at a 46 kilometers span, not 5.6, but 46, an entity nearly ninefold wider, equating to around 700 times the volume, assuming comparable density. Experts probed what this mismatch could signify. One theory posits that spherex picked up sunlight bouncing off a huge dust veil, not the core proper. Should 3I/Atlas be enveloped in an immense dust shroud, tiny grains in total forming a colossal haze, they might scatter sufficient infrared to render the setup look 46 kilometers wide. Still, this idea revives the earlier snag. What about the tail? Sunlight's push on particles drives them sunward. A dust veil vast enough to feign a 46 kilometers core would yield a dazzling tail evident in all visible light shots. But most records reveal scant tail activity. The other option, the one clashing with the numbers, holds that the core truly spans 46 kilometers. With a solid ice-like density near 1g/cm superscript 3, calculations put the mass above 33 billion tons. This served as Lowe's baseline minimum. Denser makeup, say with ample stone blended into the ice, would push the mass way higher. Now reflect on detection patterns. The Atlas Array has scanned the heavens for more than 10 years, targeting close-approaching bodies and fleeting events. Across that span, we've spotted 3 interstellar visitors. Oumuamua clocked in at roughly 100 m across, about the length of a football field. 2I/Borisov hit around 1 kilometer. Then 3I/Atlas, possibly 46 kilometers. That's a 46-fold size leap, signaling about 1 million times the mass. Natural size spreads usually obey power law rules. Tiny items vastly outnumber the big ones, exponentially so. This pattern applies to asteroids, comets, planets, even stars. In sampling any group, you'd expect a slew of small finds per large discovery. The exact proportion shifts by category, yet the trend stays steady in diverse cosmic settings. Assuming interstellar wanderers adhere to such a scheme, we'd anticipate spotting hundreds or thousands of 1-kilometer types like Borisov prior to a 46 kilometers behemoth akin to what 3I/Atlas could be. The odds of the lineup we've seen, one tiny, one middling, followed right away by a colossus, defy any sensible size-frequency framework. That is, barring flawed data, or 3i/Atlas not truly being 46 kilometers, or the infrared data misreading the body's traits or shape. This loops us to pondering just what's emitting that infrared glow. A theory floats that 3i/Atlas could be a rubble aggregate, a loose assemblage of minor chunks instead of a unified solid. Such fragmented builds prevail in asteroids, along with certain comets. These structures arise as gravity binds loose debris into a cohesive body, though not merging it completely into a dense rocky core. Spaces amid the debris generate hollow spaces inside. As such a comet nears the sun's warmth can sublimate ices buried deep in its makeup, building pressure that pushes vapors out via openings on the exterior. Should 3i/Atlas turn out to be a porous rubble pile, its apparent diameter might seem substantial even if its overall weight stays relatively light. Picture a tightly packed snowball next to the same amount of fluffy, unpacked snow. The dense one feels heavy and solid. The scattered version fills the identical volume, yet holds far more empty space and far fewer solid bits. Thus, a 46 kilometers rubble aggregate might weigh about as much as a 10 kilometers solid core if the average density drops low enough. Yet these loose assemblies also influence reactions to heat strain. The empty pockets act as barriers to warmth. Thermal energy spreads less readily through them. Gas release might erupt more forcefully since pressure accumulates inside prior to bursting through outlets. Telltale signs distinguishing a rubble pile from a compact core show up in nuanced, quantifiable differences. Analyses of vapor output speeds, heat radiation profiles, shifts in spin behavior. All these offer hints into the hidden makeup. To date, data on 3i/Atlas hasn't decisively supported one view over the other. The sharp rise in cyanide output nearing the sun points to a heat-triggered reaction. Still, linking that to either a monolithic or fragmented build stays unclear. The odd makeup, rich in carbon dioxide but sparse in water, might stem from origins in an especially chilly zone of a far-off protoplanetary disk. Alternatively, it could reflect heavy alteration, say from prolonged cosmic ray bombardment en route through interstellar space or via another process. One more perspective warrants examination. Suppose 3i/Atlas hides a firm central body enveloped in a vast but flimsy shroud of particles. Not the classic gaseous and dusty halo, but a more organized layer. Certain comets display dust lanes, trails of bigger grains trailing along the orbit. Such paths can stretch millions of kilometers, yet stay too spread out to form prominent tails. If 3i/Atlas is dispersing matter in a specific manner, forming a shell of grains orbiting with the core, that sheath might bounce back infrared rays to inflate the perceived scale beyond the true nucleus size. The issue with these ideas is their post hoc tailoring to match findings. We spot oddities, then craft theories to account for them. Without fine-grained imaging to visualize the proposed features, sorting rival theories proves tricky. The October Mars close approach was meant to deliver that detail. Heroes promised 30 kilometers per pixel view ought to have depicted a 46 kilometers body as a clear disk, not just a dot. Details like overall shape or even terrain might have emerged if the clarity held up. Yet those visuals are absent. Or more accurately, they're likely tucked away in NASA's repositories, awaiting release. European shots from Cassini fall short on sharpness to settle the dimensions debate once and for all. Thus, ambiguity lingers, spanning a ninefold gap from minimal to maximal size guesses, a span that flips the odds and reshapes what 3i/Atlas signifies physically and statistically. Lowe tackled this haze in his lectures and articles. He stressed how size fixes from fresh data, especially if NASA shares the prime stuff soon, will prove vital in testing if 3i/Atlas aligns with standard comet groupings. A tiny core below 10 kilometers dilutes the odds-based case. We could chalk it up to an oddly luminous wanderer with quirky elements, yet essentially ordinary. A hefty one nearing 46 kilometers bolsters the improbability claim. It strains against fitting as a typical interstellar stray. This ties into the larger puzzle of interstellar visitors' frequency. Pre-Oumuamua, models offered guesses sans real sightings. Spotting 3 in 8 years sketches a basic tally of their cosmic abundance. Factoring in detection biases and scope constraints, experts figure perhaps one lurks inside Earth's path anytime. Venture outward and counts climb. Near Neptune, maybe scores. In the Oort clouds reaches thousands. These projections hinge on certain assumptions regarding size variations. Should the majority of interstellar visitors turn out to be compact, the overall density in space might prove greater. Conversely, if larger specimens dominate, the density would need to be reduced to align with the detections we've recorded. The data weave together a network of limitations. Alter a single premise, and you'll have to recalibrate the rest to stay in line with our actual observations. The third find, known as 3I/Atlas, highlights this intricate network due to its unclear dimensions. Encountering a 46 kilometers interstellar body as our third sighting doesn't fit the expected pattern. In probabilistic terms, we'd anticipate discovering numerous smaller ones initially, long before chancing upon such a behemoth. Spotting what could be a colossal object in third place implies either remarkable fortune on our part, which remains a possibility, or that the assumed size profiles are off the mark, or perhaps the entity isn't quite what it seems. That final option continually revives talks of an artificial origin. If 3I/Atlas is engineered, if it's a manufactured structure instead of a standard comet, then size-based probabilities lose their grip. An interstellar-capable society would craft vessels in sizes tailored to their needs. They wouldn't be bound by the galaxy's natural scattering of frozen debris. A 46 kilometers vessel might seem excessive from our perspective, yet we lack any benchmark for extraterrestrial design norms. Naturally, arguing for artificiality based on deviations from natural stats creates a blatant loop in logic. We simply don't possess sufficient evidence to define reliable statistical norms yet. Just 3 spotted over 8 years yields a mere trio of samples. Forming definitive views on overall distributions from so little is, at minimum, hasty. Yet this very shortfall fuels the irritation. We require additional information. We demand superior scrutiny. We crave the in-depth visuals and spectral analysis that various probes were set to deliver back in early October. Instead, we're left twiddling our thumbs as ponderous organizations navigate their bureaucratic hurdles, hampered by financial and ideological barriers. All the while, 3I/Atlas presses onward. It has passed Mars' path. It's nearing its closest solar approach. Before long, it'll slip behind the sun, invisible from our vantage, pursuing whatever activities comets, probes, or mysteries engage in unobserved. The matter of its mass stays unsettled. The dimensional uncertainty lingers, and the probabilistic cases for or against a natural source hang in limbo, pending evidence that might, or might not, forthcome. Chapter 5. The Matter of Origins. From whence did 3I/Atlas originate? Not merely its path slicing through our solar system, that's firmly mapped, but the profound query of the stellar birthplace that ejected this wanderer eons past. Backtracking interstellar drifters to their roots poses formidable obstacles. These relics have roamed the galaxy for ages, buffeted by stellar gravitational tugs, clashes with gas clouds, and the ongoing twists of galactic spin. Even minor errors in present-day speed readings balloon wildly when projecting rearward across millions or billions of years. Researchers under Matthew Hopkins at the University of Oxford addressed this via the Otoroho-Oxford framework, an advanced simulation merging insights from the Gaia Space Telescope's star catalog with simulations of young planetary disk compositions and broader galactic motions. They fed in 3I/Atlas's noted speed and location, then reversed its course across time, noting potential close stellar encounters along the way. Central to this is the speed factor. Upon entering our system, 3I/Atlas was receding from the Milky Way's core at 51 kilometers per second against the Sun. It also ascended perpendicular to the galactic disk at 18.5 kilometers per second. That perpendicular rise, the W component in galactic terms, stands out as elevated. Local stars and solar neighborhood items generally show milder vertical drifts, often below 10 kilometers per second. Disk dwellers circle largely flat with modest oscillations, but 3I/Atlas's upward push surpasses routine fluctuations. This points to membership in the thick disk group, not the thin one, as per astronomical classification. Our galaxy's disk features dual layers. The thin disk hosts fresher stars, those rich in metals, akin to the Sun, tracing a fairly level orbit. The thick disk harbors ancient ones, metal-scarce, born in the galaxy's formative, less processed era, following paths more spread vertically. Thick disk items often display amplified vertical speeds owing to their orbit's angles against the primary plane. Should 3I/Atlas hail from the dense galactic thick disk, this object appears to be quite ancient. Researchers led by Hopkins calculated its age at roughly 7.6 to 14 billion years, with 68% confidence. By comparison, our Sun clocks in at 4.6 billion years. The comet 3I/Atlas could even outdate the whole solar system by several billion years. It probably originated when the universe was only about half as old as it is now, serving as a remnant from a bygone era in the Milky Way's past. A separate study by Astor Taylor and Daryl Seligman drew comparable results, pegging 3I/Atlas at 3 to 11 billion years old. Such a broad span arises from the need to make educated guesses about the thick disk's development and dynamics when turning motion data into age figures. Still, both teams concur that 3I/Atlas is a primeval relic, one that's roamed the galaxy for an impressively extended period. Its elemental makeup reinforces this view. Stars in the thick disk show reduced levels of metals compared to those in the thin disk. In astronomical terms, metallicity measures the presence of elements beyond hydrogen and helium. The primordial cosmos consisted almost solely of those two lightweight gases. As stars burn through them, they produce denser atoms like carbon, oxygen, nitrogen, silicon, and iron. Upon their demise, particularly in explosive supernovae, these stars disperse the heavier stuff into the space between stars. Later star batches and planetary setups emerge from gas enriched by these metals. Because thick disk stars ignited sooner, they incorporated fewer of these enrichments. Any worlds or icy bodies born there would mirror those leaner conditions. Should 3I/Atlas have coalesced in a metal-scarce disk around a young star, its makeup would stand apart from comets in our solar system. The elevated carbon dioxide relative to water content could signal origins past the CO2 snow line, within a disk featuring unique thermal and compositional profiles. These clues all suggest 3I/Atlas hails from an elderly stellar setup in the thick disk. Yet pinpointing the exact host star remains elusive. Investigators under Yang Guo worked to rewind 3I/Atlas's path across the galaxy, seeking likely origin points. Drawing on Gaia observations of more than 13 million stars, they ran models to spot which ones 3I/Atlas might have approached closely over the last 10 million years. Close here equates to roughly 6.5 parsecs. At such proximity, a star's pull could sway an object's path sufficiently to bind it gravitationally or fling it outward. The models flagged 93 potential close passes along its backward traced route. Among them, 62 held up at the 2 sigma threshold, where trajectory errors didn't fully dismiss the possibility. The catch? Not one of these brushes caused notable disruptions. The most promising candidate, listed as Gaia DR 3686-3591-1313-895-296-11264, came within 0.3 parsecs of 3I/Atlas at a closing speed of 35 kilometers per second. Even so, the velocity shift amounted to just 0.00051 km/s, or about 0.5 meters per second. That's trivial. For context, 3I/Atlas hurtles along at 60 kilometers per second nowadays. A tweak of half a meter per second barely registers. In short, no star zipped by in the last 10 million years, even out to 500 parsecs from the Sun, explains 3I/Atlas's present course. The comet wasn't booted from a neighboring system anytime recently. Instead, it's traversed the voids between stars for far longer, maybe hundreds of millions or billions of years. This paints a captivating yet humbling scene. 3I/Atlas embodies the ultimate drifter. It took shape near some unidentified star eons ago. Then, tugs from gravity, likely a massive planet or a stellar near-miss, ejected it from home. Ever since, it's meandered across the galaxy, grazing other systems like ours now and then, but spending most time in the immense voids. Along the way, high-energy particles from space have pummeled its exterior. Tiny interstellar specks have eroded it like grit. Far-off stellar radiation has reworked its outer layers chemically. Such exposures gradually modify the body, potentially obscuring its primal makeup. That's why likening 3I/Atlas to our local comets offers just partial clues. Those solar ones stay untouched, tucked away in chilly reserves like the Oort cloud or Kuiper belt since the system's birth 4.6 billion years back. 3I/Atlas, by contrast, has faced the interstellar harshness for possibly triple that duration. Its thick disk roots also spark curiosity about its birthplace environment. Thick disk stars frequently host orbiting planets, as shown by Kepler and various exoplanet hunts around low-metal hosts. But the structures of planetary setups around stars with lower metallicity vary significantly from those orbiting metal-abundant stars. Reduced metallicity implies fewer solid elements for planet building. As a result, terrestrial worlds could turn out smaller or less frequent. Giant gas planets may develop in altered ways. The overall layout of these systems, including planetary separations and sizes, ties directly to the host star's metallicity. Should 3I/Atlas have originated in a metal-poor environment, it could exemplify the icy remnants common in thick disk systems, distinct from the thin disk configurations like our own. Its odd makeup might actually be standard for its group, though it appears bizarre next to the familiar elements in our solar system. Still, these ideas are purely conjectural. We lack the ability to pinpoint its origin star with certainty. Rebuilding the precise path of 3I/Atlas's travels eludes us. What we can do is assess its present speed and deduce its group affiliation, thick disk or thin disk. Yet the exact tale of its origins and the events it endured stays buried amid the random flows of galactic motion. Certain scientists have investigated potential links between 3I/Atlas, Oumuamua, and Borisov. They might have been hurled from the identical stellar setup at separate moments, or perhaps splintered from one massive comet. However, their paths don't align with that idea. Oumuamua and Borisov approach from entirely separate angles, bearing unique velocity profiles. 3I/Atlas's trajectory stands apart as well. None of these three trace to a shared source in the galaxy's recent past. They stand as separate travelers, each bearing its distinct narrative. This separation, in fact, bolsters the argument that interstellar wanderers abound. Spotting three unrelated intruders over just 8 years implies the galaxy teems with such drifters. The voids between stars hold no emptiness. They're rife with rocks and frozen chunks, remnants from countless planetary realms in the Milky Way, all meandering along individual routes, now and then brushing against setups like ours. The majority of these are far too tiny for detection. We only catch those that swing near enough, boast sufficient size or activity to bounce back enough light for our scopes. Our spotting limits skew the record toward bigger, more luminous finds. In truth, the full array encompasses far more diminutive items that escape our view entirely. This shapes forecasts for upcoming finds. The Vera C. Rubin Observatory, once known as the Large Synoptic Survey Telescope, plans to launch full-scale work by late 2025. It will scan the whole observable sky every few nights, logging all shifts and motions. Its reach and precision should uncover numerous additional interstellar items, possibly scores annually at peak performance. Such forthcoming observations will at last yield the data volume required to properly profile these interstellar groups. We'll gauge their size ranges, speed patterns, and makeup varieties. We'll spot the unusual cases alongside the typical ones. We'll craft classifications for these cosmic transients, much like our schemes for local asteroids and comets. In this light, 3I/Atlas serves as a trailblazer, one of the initial arrivals preceding the tools for broader contextual analysis. That renders it both captivating and aggravating. Captivating, since with a mere trio in hand, each trait counts doubly. Aggravating, as decoding those traits absent a wider dataset demands informed speculation. Yet 3E Atlas's antiquity injects a deeper reflective layer into the mix. At 10 billion years, it arose in an era when the cosmos appeared altogether different. The Milky Way was more youthful and turbulent, buzzing with star birth across its plane. Galactic collisions and unions happened far more often. The universal backdrop shifted in profound manners. Such an ancient relic has observed the galaxy's transformation. It's roamed the void longer than Earth itself has endured. Our whole solar neighborhood, our world, the sweep of life here, all we cherish and understand, unfolded as 3 Atlas was already venerable, already roaming the stellar expanses. That viewpoint carries a profound humility, confronting a herald from the remote epochs, from realms and times beyond our reach, though we can faintly piece them together via astronomical insight. Should 3 Atlas possess a voice, or if we could unlock the complete chronicle etched in its makeup and form, what secrets might it reveal? Which suns has it skirted? What spectacles has it beheld? Has it ventured into alien planetary realms prior to ours? Might other societies have noted it, even probed it as we're striving to do today? These inquiries dip into the realm of fancy, yet they hold scientific spark. They drive the every observation and dataset contributes to piecing together the past of these cosmic wanderers from beyond our solar system. In many ways, we're like cosmic excavators, scrutinizing relics from remote eras and regions, deciphering narratives encoded in the laws of matter and energy. Chapter 6, The Waiting Watchers. On December 2nd, 2025, ESA's JUICE probe initiates its monitoring mission targeting 3I/Atlas. At that point, the comet will have swung past its closest solar approach, come out from the sun's glare, and reached peak activity levels. The intense solar warmth near perihelion ought to spark the strongest release of gases. Should 3I/Atlas prove to be a typical comet, December's view will reveal its spectacular display. A vivid envelope of dust and gas, a striking tail, and perhaps chunks breaking off if heat overwhelmed its fragile body. JUICE, officially the Jupiter Icy Moons Explorer, was built primarily for probing Jupiter's major satellites, Europa, Ganymede, and Callisto. Its goals involve hunting for hidden water worlds beneath icy surfaces and evaluating prospects for life. The onboard tools feature imaging devices, spectral analyzers, a radar system, magnetic field sensors, and particle analyzers, all fine-tuned for icy terrain studies and signs of livable conditions. Yet, come November 2025, JUICE happens to be ideally located to catch sight of 3I/Atlas. The probe will deploy various instruments for the task. Janus, the Jovian Advanced Moon Imager and Spectrometer, its name evoking a mythical all-seeing figure around Jupiter, is a visual imaging setup with 13 color filters spanning 360 to 1080 nanometers. It grabs multicolored photos and conducts simple material breakdowns via light reflection patterns. MAGIS, the Moon's and Jupiter Imaging Spectrometer, spans visible light into the infrared, offering sharper breakdowns of surface makeup compared to Janus. The UVS, or ultraviolet spectrometer, probes glows in the extreme and far ultraviolet ranges, ideal for spotting key compounds such as H2O, CO, and H. Rounding out the suite is PEP, the Particle Environment Package, which includes 6 sensors tracking electrons, ions, and neutral particles over broad energy scales. As a comet vents material, those expelled particles clash with the sun's wind. Some become charged by UV rays from the sun. Others swap electrons in reactions. This creates a tangled particle zone around the comet that PEP can profile, uncovering gas release rates and makeup details beyond what visible light views reveal alone. What gives JUICE an edge over ground telescopes during this period boils down to positioning. Early December sees 3I/Atlas reappear from solar conjunction, observable from Earth once more, though the sightline remains limited to a single vantage. JUICE, orbiting elsewhere amid the planets, views it from an offset angle. Blending Earth views with those from JUICE allows a 3D model of the comet's hazy sheath. Picture assessing a cloud's full volume while staring straight up at it. You get a flat outline, a shapeless smudge overhead, without grasping its thickness or reach. Introduce a sideways perspective, and the full spatial layout snaps into focus. Multiple viewpoints like these transform mere outlines into detailed volume renders. Moreover, JUICE catches 3i/Atlas right after perihelion, when it might ramp up activity beyond what Earth's scope saw in late summer or fall. If the solar close-up boosted gas jets, intensified outbursts, or altered the envelope's hue or ingredients through heat effects, JUICE will capture those shifts in their early stages. That said, there's a key limitation we've noted. The findings won't reach us until February 2026, a full 3 months post-observation. In the interim, global watchers will follow 3i/Atlas via Earth telescopes, contrasting its behavior after perihelion with what came before, flagging shifts, oddities, or path drifts from forecasts. JUICE's input will later enrich the picture, though without live updates. Terrestrial tracking picks up as 3i/Atlas pulls far enough from the sun's sky position. Scopes with 8-inch mirrors or bigger ought to spot it at the expected brightness. Teams of hobbyist stargazers, alongside pro facilities, will chart it each evening, gauging luminosity, watching for flares, verifying if its path aligns with models. Here, everyday enthusiasts step up big time. When official budgets tighten, agencies lag, or exclusive data holds back sharing, these volunteers bridge the void. Free from red tape, they control their gear. Amateurs share their findings openly on the internet. This worldwide group of hobbyist skywatchers, linked via online forums, social networks, and joint tools, operates like a scattered telescope array that covers various time zones and parts of the globe. Take Simeon Schmaus, for instance. He handled the Perseverance navcam photos before. He has no ties to NASA or ESA. He's no trained expert in planetary science. Instead, he's a passionate astrophotographer skilled in handling images, adept at pulling subtle details from cluttered data, and committed enough to invest hours perfecting methods. During the government shutdown, when NASA's processing system hit a snag, individuals like Schmaus jumped in, grabbing unprocessed files, combining exposures, and distributing outcomes. Over the last 20 years, this opening up of astronomy has sped up immensely. Advanced tools for refining images, which used to demand costly high-end computers, now work fine on everyday laptops. Automated telescope trackers that once ran into tens of thousands of dollars are available for just a few hundred. Detectors capable of spotting dim targets, previously limited to elite observatories, are now fitted to home setups. The hurdles to getting involved have crumbled away. Grab an 8-inch Schmidt-Cassegrain scope, a solid CCD imager, a computer loaded with analysis programs, and you're ready to make real contributions. Sure, you can't rival Hubble's sharpness or the power of pro-grade gear, but your captures build into the bigger picture of knowledge. And when scores or even hundreds of backyard enthusiasts worldwide train their gear on one spot, the combined info turns impressive. 3i/Atlas is bound to draw that level of focus. The debate, the guesses, the quiet from officials, it all stirs curiosity. When folks get invested in a celestial body and crave explanations, they pour effort into it. Hobby groups will organize viewing efforts. They'll swap optimal viewing slots. They'll refine one another's raw files. They'll discuss their sightings. Should 3i/Atlas act oddly, these watchers will spot it. If its glow flares up unexpectedly, somebody will detect it fast, within hours. If its path strays from forecasts, fans of orbit calculations will highlight the mismatch. If it splits into several bits where there was just one, pics will record the split. The international setup ensures backups. There's no weak link. The thing can't slip into official hush when countless unaffiliated gazes are fixed on it. Still, skywatchers can only catch what's evident post-perihelion. That key phase, the swing behind the sun, when heat strain hits max, and any imagined adjustments or satellite releases would make the most sense. Earthbound views miss that instant. Follow-up info will piece together events, but with a 3-month lag. Early after perihelion checks will reveal effects, not origins. That poses a puzzle for explanation. Imagine 3i/Atlas comes out on a path just a bit off from expectations. Not a huge shift, merely a deviation of a few tenths of a percent. Such a tweak might stem from gas jets bursting from the core, generating minor pushes. Across days and weeks, these build up to detectable speed shifts, a phenomenon known as the rocket effect that's common in comets. With that effect in play, how do you tell apart routine gas release that nudges the path a touch from intentional steering that apes normal venting? You can't, not definitively. You could simulate anticipated venting from sun warmth and core dimensions. You could gauge real venting through the haze's glow and spectral signatures. If the spotted venting matches the path shift, chalk it up to nature. If the shift outpaces what venting alone explains, flag it as unusual. Yet readings carry errors. Simulations rely on guesses. Sorting real patterns from glitches demands precise work. Or consider if 3I/Atlas breaks apart. Comets do that fairly routinely. Heat builds fissures. Spinning adds outward pull. Trapped vapors building inside exploit flaws and rip things open. If 3I/Atlas shows up in chunks, is it standard breakup or a planned split of a main craft from smaller ones? Once more, extra clues are needed to sort it out. Organic debris follows paths set by the split's layout. Bits drift apart gradually, usually at speeds under AM/s. Purposeful units might part faster. They might adjust paths solo afterward. They might show unusual pulls beyond gravity. Natural fragments wouldn't display those distinctive markers. However, spotting such indicators demands meticulous astrometric measurements spanning long durations. It's essential to monitor the location of every piece with exceptional precision, evening after evening and week by week, accumulating sufficient information to construct orbital simulations and identify irregularities. This loops back to comparing the strengths of established institutions against those of citizen-led science efforts. Expert observatories deliver the exact astrometric detail required for these examinations. The imaging systems employed in near-Earth asteroid monitoring programs, such as the Atlas system, attain positional resolutions down to parts of an arcsecond. Across several weeks of monitoring, this level of detail allows for orbital calculations precise enough to forecast locations months or years ahead and to spot minor non-gravitational influences. In contrast, typical amateur gear struggles to reach that standard. A standard 8-inch scope could manage astrometric results of 1 to 2 arcseconds in optimal setups, yet that's roughly 10 times less accurate than elite professional tools. For prominent targets drifting gradually through the heavens, hobbyist measurements work fine. But for dim, fast-moving items where tiny discrepancies demand sharp detection, expert facilities are indispensable. That's precisely why the lack of institutional response is significant. Should NASA and ESA share their findings swiftly, should leading observatories organize joint viewing initiatives, and should the Worldwide Astronomy Network deploy its complete arsenal, we'd optimize the insights from this uncommon event. Conversely, if information stalls, if monitoring lags, or if collaboration falters, our understanding suffers. The Galileo Initiative, headed by Avi Loeb, seeks to close this divide. It runs 3 dedicated sites, one in Massachusetts, another in Pennsylvania, and a third in Nevada, fitted with gear tailored to identify and analyze unusual airborne events. These facilities employ arrays of cameras spanning visible and infrared spectra, plus weather monitors to link sightings with environmental factors. Although the Galileo's main aim centers on unidentified aerial phenomena, UAP, within Earth's skies, the setups are also capable of following celestial bodies. Loeb indicated that the Massachusetts site will scan the skies before, during, and after 3I/Atlas's closest solar approach, searching for any linked surge in UAP occurrences. The idea under scrutiny posits that the entry of an extrasolar visitor could spark follow-on effects, perhaps via unfamiliar natural mechanisms or even imagined probe launches. This ventures beyond standard astronomical inquiry into hazier realms. Mainstream experts might contend there's no basis for linking interstellar comet transits to sky-based oddities. Yet Loeb's method emphasizes gathering evidence and examining it objectively, avoiding preconceived outcomes. Should no link appear, the records will confirm it. If one does, it calls for deeper probing. Ultimately, 3I/Atlas has sparked diverse monitoring approaches, from elite pros and enthusiasts to specialized endeavors like Galileo. The comet has drawn interest far beyond routine sightings. Some of that arises from its otherworldly source, some from its puzzling traits, some from the surrounding debates and theories. Together, these factors guarantee that as 3I/Atlas reappears from solar seclusion, countless observers will be tuned in. Chapter 7. The Arena of Scientific Debate. Jason Wright runs a weblog titled AstroWright, where he chronicles his astrophysics research and from time to time evaluates peers' contributions. In July 2025, he released an in-depth breakdown of Avi Loeb's assertions regarding 3I/Atlas. The entry's heading, Avi and 3I/Atlas, hints at the straightforward confrontation ahead. Wright pulls no punches, labeling Loeb's extraterrestrial craft idea as baseless and methodically dismantling every purported irregularity. As an astronomy and astrophysics professor at Penn State University, head of the Penn State Center for Extraterrestrial Intelligence, and participant in various expert panels, Wright's expertise in hunting for technosignatures, indicators of advanced societies, rivals or surpasses Loeb's. Thus, when Wright challenges Loeb's efforts, it stems not from outright rejection of unconventional ideas, but from a fellow specialist contesting the approach and findings. At the heart of Wright's assessment lies Loeb's treatment of data. Wright reviews Loeb's shifting positions on 3I/Atlas in sequence. On July 2nd, his initial online entry buzzed with enthusiasm over the find, without a whisper of alien tech. By July 3rd, in a Daily Mail feature, the notion of alien origins surfaced. On July 4th, Loeb was positing that the entity had to be far tinier than initial estimates. Initial assessments indicated that the scenario was statistically unlikely. On July 7th, Avi Loeb explored potential interception strategies during discussions. By the middle of July, he had embraced the idea that Oumuamua could be of artificial origin. According to Wright, this sequence demonstrates biased thinking. Instead of letting the evidence guide him to an outcome, Loeb settled on a preferred result up front and emphasized supporting data while downplaying or ignoring contradictory findings. For example, several observatories recorded emissions near Oumuamua, along with gas and dust forming a noticeable coma. Loeb first recognized this, but later contended that the sightings were ambiguous, suggesting the haze observed might stem from equipment glitches or image blurring due to movement rather than real gas release. The Very Large Telescope produced photos distinctly displaying a balanced coma encircling Oumuamua, precisely the pattern associated with comets. Loeb rejected these as unreliable because of the object's speed and resulting distortion, yet Wright highlights that the VLT researchers deliberately adjusted for motion in their analysis. The resulting visuals were not distorted byproducts. They depicted authentic cometary behavior. Wright also tackles the debate over dimensions. Loeb stressed early luminosity-based calculations estimating 10 to 20 kilometers in diameter, claiming it exceeded typical sizes for interstellar comets. However, as Wright observes, such figures were rough approximations relying on unverified assumptions about albedo. Later data pointed to more compact dimensions. Loeb subsequently focused on SphereX's infrared readings implying 46 kilometers, using it to underscore the object's oddity. Yet Wright challenges if those infrared signals truly reflect the core's extent or merely an surrounding envelope of dust. In his overall analysis, Wright stresses that each purported unusual trait of Oumuamua admits reasonable natural interpretations. The absence of a clear tail might arise from the observation angle or from viewing the body prior to major gas emissions. The atypical makeup, dominated by carbon dioxide and lacking water, is uncommon yet documented in prior cases. The path's closeness to the ecliptic is improbable but feasible. Probability assessments gauge chances, not absolutes. Rare events occur. That's the essence of rarity. It signifies uncommon, not prohibited. Wright's irritation surfaces when he examines the impact of Loeb's approach on technosignature studies at large. Researchers like Wright, engaged in extraterrestrial intelligence hunts, must uphold scholarly integrity. They require support from grant providers who view their ideas credibly. They depend on outlets to accept their submissions. They rely on peers for partnerships. When prominent figures advance daring assertions on scant proof, it tarnishes the whole discipline's standing. Detractors can cite such excesses to contend that technosignature work is fundamentally frivolous, perpetually favoring sensational theories over disciplined inquiry. This sparks friction in the SETI realm. Visibility is essential for the area. Public fascination secures resources, press exposure draws learners, and striking suggestions of alien relics spark interest that routine reports cannot match. Conversely, legitimacy demands recognition as sound scholarship, free from eccentric conjecture. Reconciling these demands fuels persistent discussions on approaches, proof thresholds, and public outreach strategies. Loeb's replies to detractors remain steady. He casts himself as a Galilean icon, an innovator defying convention. He maintains that conventional science clings too tightly to caution, hastily rejecting novel concepts, and safeguards entrenched views. He recalls how history's paradigm-shifting thinkers endured opposition before ultimate validation. The implication is that his skeptics mirror those who scorned Galileo, upholding obsolete frameworks against jarring realities. Such framing carries persuasive force. Underdog tales appeal widely. The portrayal of an isolated scholar doggedly chasing facts amid systemic resistance strikes a chord. Still, Wright and fellow critics deem it deceptive. Loeb faces no suppression. His articles appear in print. He occupies an esteemed role at Harvard. He directs generously backed initiatives. He features often in outlets. In truth, he garners more spotlight than typical academics. The resistance he encounters arises not from a stifling establishment, but from experts identifying issues in his methods. Critique forms part of the scholarly method. Proposing a theory invites scrutiny, verification, and flaw detection from others. That's the mechanism driving advancement. Colleagues challenging Loeb's assertions regarding Oumuamua simply exemplifies this norm. Critics aren't being narrow-minded when they scrutinize the evidence and propose other explanations. It's simply part of their role in science. While certain critiques come across as abrasive or offhand, a good portion delves deeply into concrete problems with the data processing or logical arguments. For instance, Chris Lintott, an astrophysics professor at Oxford, labeled Loeb's idea of the three-eye atlas as an alien probe as utter rubbish. He pointed out that, after considering the constraints of observations and uncertainties in analysis, every piece of data supports viewing 3 Atlas as a standard comet exhibiting conventional cometary traits. Fellow astronomers have voiced similar opinions, whether openly or behind closed doors. In the planetary science field, the prevailing opinion holds that 3-eye atlas is a natural phenomenon. Yet, agreement among experts doesn't guarantee truth. Scientific findings are always tentative, open to change with fresh data. It's quite conceivable that the dominant perspective could turn out to be incorrect. Past cases show how established views in science have been overturned eventually. The theory of continental drift faced rejection for years until plate tectonics won over the community. Prion, those infectious proteins lacking nucleic acids, were deemed implausible until Stanley Prusiner proved otherwise. Doubts about extrasolar planets persisted right up until the 1990s confirmations. This raises the key issue. What kind of proof would be enough to challenge the widespread belief that 3-eye atlas is natural? Which sightings or data points could persuade the doubting experts to take artificial origins seriously? Loeb outlined a few benchmarks. Evidence of maneuvers by 3 Atlas that don't align with typical outgassing from a comet would carry weight. The ejection of separate objects that then move on their own would almost seal the deal. Detection of radio waves or electromagnetic outputs not matching mere heat emissions would make a strong case. High-resolution pictures showing symmetrical shapes, repeating designs, or signs of engineering would require addressing. So far, none of these indicators have appeared. 3 Atlas has stuck to its expected path, with deviations explainable by natural venting. It produced no odd transmissions. Imagery lacks any manufactured features. In nearly all observable aspects, the body acts just like a comet. The quirks stand out only in its chemical makeup, which, though uncommon, has natural causes, and its path's odds, which are slim but feasible. Under these conditions, the majority of astronomers invoke Occam's razor to back the ordinary account. Among rival ideas that fit the facts, go with the least complicated. A comet boasting rare yet earthly qualities is less convoluted than an extraterrestrial vessel crafted to imitate one. The artificial theory piles on prerequisites. Sophisticated societies must thrive out there, master travel between stars, opt to explore our neighborhood, build probes resembling comets, and arrive precisely when our detection tech is up to the task. That's an imposing tower of suppositions. By contrast, the everyday theory just needs interstellar comets to be real, which we've spotted 3 times already, and for some to display atypical traits, a reasonable outcome from the varied ways solar systems form galaxy-wide. Far less baggage, so it wins out without standout counterproof. Loeb might respond that such logic assumes we grasp the odds for all these elements. How solid is our conviction that extraterrestrial societies are scarce? Can we truly gauge the challenges of star hopping? Do we comprehend what drives an advanced species? The Copernican principle, that humanity isn't the center of everything, implies other intelligent life likely pops up elsewhere. The Fermi paradox highlights the puzzle. If they're probable, why no signs despite the vast cosmos? One answer could be that they interact or journey in methods we've overlooked. Passing interstellar visitors might represent such an approach. This deeper philosophical clash over starting assumptions shapes the heart of the dispute. Scientists entering with varying preconceptions draw divergent verdicts from identical observations. Experts starting with slim odds on alien tech demand massive proof to shift views. Those leaning toward higher odds, like Loeb, adjust faster to unclear signals. No method fully erases subjectivity here. Bayesian reasoning, the tool for refining beliefs via data, hinges on initial probability estimates. And where do those originate? Partly from past records and findings, but at root from subjective assessments of likelihoods. Scientists often clash over those subjective assessments, sparking disputes on how to interpret findings even when they concur on the basic data. What's aggravating everyone is the absence of solid proof. Had the Mars flyby photos been made public right away, and if they displayed sharp, intricate features, a lot of the controversy could have been resolved. If we had the chance to observe from the ground during its closest solar approach, or if we could monitor 3-2 Atlas steadily throughout its peak activity, we'd gain tighter limits on possibilities. As it stands, we're stuck with fragmented info, postponed disclosures, missing coverage periods, and ample space for rival explanations to linger. The ongoing scientific skirmish surrounding 3-2 Atlas highlights the realities of astronomy when tackling infrequent, scantily documented events. It's far from tidy. It's rarely conclusive. It's a chaotic exchange of rival theories, patchy proof, expert clashes, and widespread conjecture. In the end, 3-2 Atlas might perform some undeniable action that compels agreement, or it could exit the solar system while its essence remains contested, just one more enigma in the extensive catalog of cosmic puzzles yet to be solved. Chapter 8. The Frenzy on Social Platforms. As experts argued over methods and proof thresholds in academic papers and online logs, a separate dialogue erupted across social networks. 3-2 Atlas shot to prominence on X, once known as Twitter, with countless entries dissecting photos, offering guesses, and disseminating false info. Reddit forums launched discussions to follow each update. YouTube producers rolled out clips bearing headlines, teasing astonishing disclosures. TikTok posters whipped up brief videos breaking down the comet or alerting to supposed risks. This sequence mirrors the usual path for celestial occurrences that seize the public's interest. First, buzz builds among pioneer groups like astronomers, space fans, and science explainers. Next, broader notice surges as media reports pick up the tale. Afterward, the storyline splinters into myriad versions as various perspectives layer in their takes, fixes, additions, and inventions. And certain social chatter stayed rooted in real sightings and expert breakdowns. Hobbyists in astronomy posted their scope shots, swapped insights on viewing slots, and explored image handling methods. Science popularizers aimed to deliver precise background, clarifying what 3-2 Atlas entails, its origins, and its appeal. Such contributions typically featured warnings about unknowns, nods to gaps in knowledge, and nods to specialist views. Yet other material drifted into wild guesses unbound by facts. Certain entries insisted 3-2 Atlas was unquestionably an extraterrestrial command vessel, referencing Avi's writings but skipping his qualifications. Some cautioned it represented an urgent peril to our planet, ignoring how its path remains well outside Mars' path. Plot theories multiplied. A few alleged authorities were concealing facts on 3i Atlas. Others tied it to disconnected happenings, like political shifts, financial forecasts, or spiritual omens. One especially widespread entry wrongly credited remarks to physicist Mikioku, asserting he declared 3i Atlas was speeding toward Earth with aggressive aims. It featured an altered capture from a TV segment. Kaku showed up on screen with superimposed words implying he voiced these bold assertions. The visuals circulated swiftly, racking up hundreds of thousands of views until verifiers exposed it as fake. The genuine interview capture dated back to February 2025, well before 3 Atlas's detection. An individual had grabbed an irrelevant Kaku broadcast, inserted deceptive wording, and floated it as fresh reporting. Such alterations occur often with science-related subjects. Prominent individuals get misrepresented or their words twisted to back stories they never backed. A laser's verification team, Sanard, probed the Kaku assertions and issued a thorough takedown. They followed the picture to its origin, verified the initial talk's timing, and uncovered zero evidence of Kaku commenting on 3i Atlas whatsoever. However, once verification surfaced, the bogus assertions had already propagated via circles of followers eager for the thrilling account. This reveals a core issue in today's info landscapes. Reality and invention travel at varying speeds via distinct routes. Dependable but ordinary details, like 3.2 Atlas being an interstellar comet on a foreseeable course that endangers Earth not at all, draw limited interaction. Outrageous but untrue details, like experts verifying an alien vessel nearing Earth with aggressive plans, spark huge interaction since they stir strong feelings, such as alarm, thrill, and intrigue. Site algorithms favor interaction. Entries that drive taps, reposts, interactions, remarks, and time spent on the platform boost visibility for posts. Material that people merely scroll by without engaging sinks into obscurity. This dynamic imposes selective pressures, prioritizing material that elicits intense responses, irrespective of its truthfulness. Producers of content, driven by sincere convictions, a craving for notice, or monetary gains from advertisements, adapt by designing posts that optimize user involvement. Consequently, an informational landscape emerges where verifiable information vies against fabrications under uneven conditions. Researchers who temper their assertions with suitable caveats of uncertainty are overshadowed by assured assertions delivering absolute declarations. In-depth examinations demanding focus and reflection yield to straightforward tales that solely trigger visceral responses. The methodical progression of scientific inquiry, formulating hypotheses, gathering data, refining ideas, and forging agreements, appears tedious and sluggish beside the swift barrages of stimulating exchanges on social networks. 3i Atlas turned into a projection screen for individuals' preconceived notions. Believers in governmental cover-ups of alien encounters viewed NASA's reticence as validation. Doubters of official institutions saw the absent visuals as deliberate suppression. Enthusiasts of end-times prophecies recast the comet as a peril, even though its path maintained a distance of millions of kilometers from our planet. A recurring storyline asserted that armed services were gearing up to redirect or obliterate 3i Atlas. Entries cited supposed troop movements, clandestine gatherings at the Pentagon, and collaborations among global security organizations. Such assertions held no evidential support. No mobilizations of that nature took place. No reliable outlets documented any armed involvement with 3i Atlas except routine monitoring of major celestial bodies through space awareness protocols. Yet the storyline endured because it aligned with certain perspectives. If 3i Atlas posed a danger, naturally the military would mobilize. If authorities suppressed data, evidently they would not publicize their strategies. The lack of proof morphs into proof of hiding. Each refutation bolsters the conspiratorial framework, since plotters would predictably disavow their schemes. This reasoning renders such ideas impossible to disprove, resistant to standard rebuttals. Certain social media participants adopted another tack, regarding 3i Atlas as diversionary fun rather than a serious enigma. Memes spread widely. A favored style featured the Doomsday Machine from Star Trek, overlaid with quips about humankind's dealings with cosmic arrivals. Another employed the Disaster Girl meme layout, inserting 3i Atlas digitally into the scene. These witty interpretations recognize the conjecture while keeping a detached, ironic stance. This playful lens fulfills a communal role. It enables involvement in the subject without endorsing particular views. One can circulate a gag about 3i Atlas as an extraterrestrial vessel without truly accepting that idea. The levity fosters shared territory, a means to join the societal buzz surrounding the find without plunging into heated arguments over authenticity. However, wit and false information lie along a spectrum. Initial clear parody might be interpreted straightforwardly by viewers missing the intent. Captures of ironic entries circulate minus background. Spoof profiles get confused with authentic ones. Lines fade between amusement, guesswork, falsehoods, and intentional misleading. Moderation squads on these networks confront tough choices. How to address entries spreading inaccuracies on scholarly subjects. If a post declares 3i Atlas an invading alien craft nearing our world, does it qualify as hazardous deceit needing deletion or shielded conjecture and viewpoint? Various sites enforce varied criteria. Some adopt minimal interference, permitting nearly all unless it sparks direct aggression or bullying. Others aim to add alerts or verification tags to suspect statements. No method eradicates the issue entirely. Strict oversight hazards stifling valid discussions and igniting accusations of partiality. Lenient oversight lets falsehoods proliferate freely. The volume, millions of entries daily over numerous sites, renders uniform application all but unfeasible. AI-driven tools detect likely infractions, yet they err, excising harmless material while overlooking true concerns. For experts examining 3i Atlas, this online frenzy adds extra hurdles. In conveying research outcomes to audiences, one contends against a torrent of competing inputs, some beneficial, most detrimental. Reporters reach out to scholars for input, but that input could appear in pieces next to unchecked guesses from anonymous online contributors, treated with similar weight. The clarity amid chaos turns daunting. Some scientists actively participate on social platforms to deliver precise details and dispel myths. A Vibe keeps a vibrant profile on X, sharing connections to his blog entries and addressing inquiries. Fellow astronomers employ Twitter chains to clarify orbital dynamics or analyze fresh sightings. Such initiatives connect with people who skip scholarly publications or astronomy sites, injecting specialized insights into realms rife with inaccuracies. Yet, interacting on social media demands significant time and effort. Researchers juggle full-time roles in education, investigations, manuscript preparation, and symposiums. Allocating hours to Twitter for answering queries and refuting erroneous assertions pulls resources away from essential duties. Not all experts possess the drive or expertise for outreach to the masses. Many opt to let their contributions resonate via established outlets instead of diving into digital arguments. This imbalance arises because individuals eager to promote dramatic assertions frequently invest more hours in social media than busy professionals do. An academic may share a factual clarification once and then shift to pressing obligations. In contrast, various profiles persist in disseminating misleading stories, replying to feedback, distributing humorous images, and sustaining their take on happenings. Sheer quantity drowns out reliability. Furthermore, consider scenarios where the expert agreement lacks clarity. Regarding 3 Atlas, specialists hold differing views on certain analyses. Lowe argues that the oddities justify exploring artificial origins. Wright maintains that earthly causes are adequate. How does one convey such discord to everyday viewers without suggesting that experts grasp nothing and all aspects remain equally ambiguous? The research process views doubt as an asset, not a flaw. Hypotheses stay tentative, open to updates with emerging proof. Degrees of assurance fluctuate based on supporting evidence volume. This subtle knowledge framework struggles to fit into social media exchanges, where people seek clear-cut responses. If an expert admits uncertainty persists, listeners may interpret it as total ignorance. Instead of seeing doubt as a candid evaluation of present understanding, NASA's handling of public worries over 3 Atlas highlights these outreach hurdles, as a widespread post circulated unfounded assertions about the comet's path and supposed peril to our planet. The organization sought to offer comfort. Their formal declaration stressed that 3 Atlas presents zero risk, its nearest pass to Earth spanning millions of kilometers, and its route being thoroughly mapped and foreseeable. However, for those distrustful of NASA, such assurances proved minimally persuasive. If one suspects official bodies fabricate tales on alien topics, then authoritative rejections hold little sway. Indeed, they could heighten doubts. This pattern locks organizations into an unwinnable bind. Staying quiet nurtures theories of secrecy. Releasing counterstatements nurtures theories of concealment. No tactic wholly resolves issues from groups with divergent ways of knowing. This overarching trend applies widely beyond 3 Atlas to outreach in science at large. Whenever an issue draws widespread interest, be it global warming, immunizations, machine learning, or cosmic ventures, the identical patterns surface. Authorities strive to supply correct data tempered by fitting reservations. Campaigners and proponents advance tailored readings that match their principles. Self-promoters seize the spotlight for profit. Theory weavers integrate it into long-standing plots. Humorists and image makers repurpose it for laughs. These varied perspectives vie for notice in a common arena where lines between authority and viewpoint blur. Perhaps remedies involve reimagining how research bodies connect with general publics. Traditional methods, news bulletins, sporadic chats, authorized pronouncements, suited an age when media overseers managed data streams. Reporters screened origins, added background, distinguished key points from distractions. That framework carried its flaws and slants, yet it offered some screening. Social media dismantled those overseers. All can broadcast straight to worldwide viewers. This openness yields advantages, varied inputs, swift data exchange, community-driven efforts. But it also introduces issues, falsehoods, deceit, automated boosting of radical material. Tailoring science outreach to this landscape stays an evolving trial with unpredictable results. Chapter 9. The December Unveiling. The start of December 2025 signals a crucial phase. 3 Atlas, concealed by the sun for weeks, will appear in spots suitable for Earthbound scopes. Its position will start low in the sky before sunrise. The comet will only be visible for a brief window of a few hours before dawn. Nearby, Venus will shine brightly and unmistakably, serving as a handy guide to spot the far dimmer comet. With an estimated brightness of magnitude 10, it hovers right at the limit of what binoculars can reveal under clear, dark skies. A seasoned skywatcher equipped with quality gear might catch it as a hazy smudge standing out against the stars, though for solid verification, a telescope is essential. An 8-inch aperture offers plenty of leeway for viewing. Bigger scopes could uncover finer details, such as the coma's shape or perhaps a subtle tail if it has started to form. What people spot in those initial evenings post-perihelion will settle key uncertainties right away. Has Comet 3I/Atlas held together? Does it look like one piece or several bits? Has its glow shifted sharply from pre-encounter records? Is a tail becoming evident? Does its path align with forecasts, or are there offsets? Sightings will pour in from scores of sites all at once. Hobbyists in astronomy groups organize watching drives via web discussions and mailing lists. Folks down under in Australia snag the earliest glimpses as the comet climbs their eastern sky. They share first impressions, rough brightness readings, and accounts of its look. A few hours on, watchers in the Middle East take over, followed by those in Europe, and then across the Americas. This handoff keeps them monitoring nonstop, compiling a steady stream of data over days and even weeks. Pro setups will pitch in too. Telescopes usually hunting asteroids will swivel toward Comet 3I/Atlas, nailing down exact spots for trajectory calculations. Labs doing spectroscopy will probe the coma's makeup, probing how the sun's closest approach tweaked the gas release patterns. Imaging gear will log changes in shine that could signal spinning or sudden flares. All this info will stream into repositories run by the Minor Planet Center, the go-to hub from the International Astronomical Union for comet, asteroid, and other minor solar system trackings. Scientists around the globe will dive into this pool, tweaking orbit simulations, cross-checking views from various tools and spots, and hunting for trends or oddities. Should Comet 3I/Atlas have split apart near the Sun, early peaks will expose several bodies in place of the original single form. Every chunk would follow its own mildly varied route, shaped by the speed and angle of the split. Following those pieces night after night would let experts piece together the timing and nature of the split. Usual breakups in comets yield fragments that spread out gradually, at just a few meters per second. The bits remain bunched up for weeks, then ease into separate paths over time. Yet what if the views reveal otherwise? What if several forms show up, but move apart faster than a typical split would allow? Or if they exhibit speed shifts not tied to surface gas vents? Those would call for deeper probes. Such ideas are still just guesses. Nothing points to Comet 3I/Atlas breaking up in the first place. Plenty of comets weather their sun dips whole, particularly when they stay beyond roughly zero. $5 at closest. At $1.36, Comet 3I/Atlas is safely past that risky threshold. Heat pressures will be intense, yet likely not destructive. It ought to reappear in one piece, barring some fragile core or unusual non-comet-like antics. Path tracking turns pivotal in December's watches. Pre-sun data-based orbit forecasts rely solely on pulls from gravity. The sun's tug leads the way, with Jupiter adding minor nudges and other worlds chipping in even less. Sum up those influences, run the motion math ahead, and you land on expected spots for later dates. Still, comets face extra pushes from gas ejections. Bursts of vapor from the core generate a small shove, nudging the speed a touch. Over periods, these build up. For ones with strong venting, skipping those forces in calculations can lead to clear location mismatches after weeks or months. To handle this, experts fold in extra push factors in their orbit fits. These include adjustable values tuned to match sightings, figuring the vent thrust as puzzles to solve alongside the core path details. When those tweaks line up with the seen gas output, and the push levels fit the gauged vapor yields, if deviations in the path surpass what typical gas release could account for, issues arise. This might mean your assessments of gas emissions are lacking, overlooking certain aspects of the activity, or that some additional force is influencing the body. That's when meticulous monitoring turns essential. Comprehensive spectral analysis is required to detect every type of gas released. Photometric tracking helps monitor luminosity as an indicator of activity intensity. Accurate positional measurements via astrometry ensure precise location data. Linking these datasets enables separating standard gas expulsion impacts from possible external factors. The December data collection will offer the initial evaluation of whether 3Atlas's course after perihelion aligns with forecasts. Information will build up progressively each evening. Following a week of monitoring, initial orbit calculations will reduce the margins of error. By 2 weeks in, the limits will sharpen even more. Come the close of December, experts will possess a firm grasp on 3Atlas's direction and any shifts from projected routes. Should anomalies emerge, specialists will scrutinize their implications. Minor shifts within bounds attributable to gas release will prompt studies on non-gravitational influences, though without sparking widespread dispute. Substantial shifts, alterations clashing with standard comet dynamics, will provoke thorough examination. Investigators will scrutinize equipment flaws, observational biases, and rival theories. Consideration of exotic ideas would only follow after ruling out routine options. In parallel, the JUICE probe will perform its independent assessments from November 2nd through 25th. These coincide with the time frame when 3I loss remains obscured by the sun from our viewpoint. JUICE will observe the comet amid and right after perihelion, recording details of its peak activity, yet that information won't arrive on Earth before February 2026. Such timing produces an odd void in knowledge. December watchers will witness the consequences without full insight into the events. They'll observe 3Atlas's condition following perihelion, lacking the in-depth chronicle of the closest solar approach. The delayed JUICE findings, arriving in February, will retrospectively bridge that void, but during the gap, analyses will depend on deduction over first-hand viewing. Imagine if December data indicates 3Atlas remains whole and follows a path fitting expected gas effects. That would bolster the standard comet model. The peculiar pre-perihelion makeup and related oddities would stay intriguing yet accountable through natural means. The narrative would probably slip from widespread interest, treating the visitor as merely another interstellar wanderer. Curious, yet not transformative. On the other hand, envision December results uncovering surprises. Several fragments replacing a single body, with spacings mismatched to typical breakup or path shifts beyond reasonable gas influences, or spectral traces unrelated to familiar comet materials. Such outcomes would revive arguments and necessitate clarification. The difficulty in handling odd findings lies in separating true irregularities from illusions. Equipment malfunctions occur. Weather influences can warp readings. Processing oversights happen. Prior to labeling an observation as verifiably unusual, everyday causes must be dismissed. This demands verification across diverse, unrelated setups with varied tools and personnel. When various groups detect identical phenomena using distinct gear and techniques, trust in its authenticity grows. During December, both hobbyist and expert viewers will inherently perform this mutual confirmation. If a single scope detects oddities while others don't, blame falls on that device's glitch. When scopes at varied sites all capture the same trait, assurance builds that it's genuine. This widespread observer array offers backup and flaw detection absent in isolated site efforts. Online platforms will magnify all detections. Each photo, datum, and analysis will circulate and spark dialogue. This yields advantages and pitfalls. The upside is swift sharing of insights. Compelling discoveries propagate fast, drawing focus and extra scrutiny. The downside is hasty or flawed claims also propagate rapidly, sowing doubt until fixes emerge. Experts favor confirming outcomes prior to public disclosure. The customary workflow entails gathering evidence, scrutinizing it thoroughly, drafting findings, undergoing peer evaluation, and releasing only afterward. This measured approach, e-science prioritizes precision at the expense of timeliness. In contrast, social platforms flip this focus, emphasizing quick dissemination over careful scrutiny. Fresh findings appear online mere hours after capture, typically with scant review and occasional guesses that stretch beyond the evidence. This clash between methodical research and societal eagerness unfolds during every major celestial sighting. The case of 3I Atlas will follow suit. Initial post-perihelion photos will spread rapidly. Viewers will magnify them, adjust brightness, hunt for details. They'll contrast these with pre-perihelion shots, probing for alterations. Assertions about discoveries will emerge, varying from spot-on to misguided. Experts in astronomy, undeterred by online chatter, will adhere to their protocols, gathering data, processing it, calibrating measurements, modeling outcomes, and sharing findings via publications and archives. That rigorous documentation will offer the definitive narrative on 3I Atlas's actions, though it arrives weeks or months following the early digital buzz. The key issue, though, hinges on whether 3 Atlas's showing in December prompts shifts in our cosmic knowledge. Should it act like a standard comet, adhering to expected physical laws, exhibiting typical gas emissions, and tracing paths aligned with gravity and propulsion influences, it reinforces our solid grasp of such wanderers. Odd compositions and improbable paths intrigue without appending theories. Yet if it exhibits inexplicable traits, necessitating ideas or mechanisms outside conventional comet frameworks, December 2025 marks a pivotal era. Spotting irrefutable signs of artificial construction in our solar system would transform fields like astronomy, astrobiology, and our collective view of humanity's cosmic role. Put simply, the implications loom large. Not for any urgent threats, 3 Atlas presents no risk, no matter its essence. But regarding insights into the cosmos and life off-world, those December glimpses could prove transformative or merely enrich our roster of extrasolar visitors. Fascinating, yet not groundbreaking. Clarity awaits the actual data. Meanwhile, conjecture persists, molded by partial info, rival viewpoints, and the aspirations or anxieties individuals overlay on this enigmatic interloper from interstellar voids. Chapter 10. The recurring motif and the quiet. Time to pull away from the nitty-gritty of spectra analysis, path calculations, and survey efforts, and reflect on the overarching trend embodied by 3I Atlas. This marks neither the debut nor the finale of a stellar find igniting talks of unnatural sources. Grasping the reasons demands scrutiny of our handling of odd data and the dynamics when organizations gatekeep details the public craves. Established set the precedent. Upon spotting the inaugural verified interstellar body in October 2017, its quirky traits swiftly fueled arguments. The cigar-like form, the extra push sans gravity as it departed our system, the absence of evident emissions amid that boost, all struck as peculiar. Avi suggested it could be a solar sail, a delicate mirror-like sheet driven by sunlight's force. The majority of experts leaned toward organic causes, likely a comet with atypical venting or a shard from a shattered form. The dispute unfolded in academic papers, mainstream outlets, and digital forums. Certain researchers voiced irritation at the alien theory, deeming it hasty and baseless. Others upheld the merit of exploring every angle, no matter how slim, amid novel sightings. The exchange exposed divides in scientific philosophy on managing vague clues for bold assertions. Twier, found in August 2019, offered a foil. It resembled a comet right from detection. Distinct haze, evident streamer, spectral matches to familiar icy blends, path shifts fitting gas-free motion. No one floated extraterrestrial ideas for Borisov, as its traits aligned with expectations. It mirrored what stargazers anticipated for ejected solar system remnants based on formation and expulsion models. 3 Atlas sits midway on this spectrum. It reveals icy vigor absent in established. Still, it bears anomalies, the compositions, path oddities, dimensional uncertainties that set it apart from garden-variety icy bodies like Boris. The pivotal debate centers on whether these quirks necessitate outlandish theories or simply highlight diversity among interstellar drifters. Beyond the particular scientific discussions, the 3I Atlas case sheds light on broader issues of data management and confidence in official sources. As NASA's Mars probes were ideally placed to snap high-resolution photos at a moment ripe for clarifying the object's composition, the federal shutdown kicked in. Perhaps that overlap was purely by chance. Perhaps administrative glitches, not intentional suppression, account for the absent visuals, yet the appearance is disastrous. Folks instinctively figure that organizations adept at orchestrating intricate orbital operations could manage photo distribution amid a funding halt if motivated to do so. The impression, right or wrong, is that officials deliberately selected which details to share and which to suppress. Such views stoke notions of hidden agendas and chip away at faith in how scientific bodies convey findings. This ties into a prolonged pattern of official reticence concerning cosmic sightings. The U.S. Armed Forces run surveillance satellites that scan our planet with remarkable clarity. Those technologies stay under wraps. The precise specs on their viewing power, image handling techniques, and surveillance targets all remain shielded by clearance barriers. The rationale? Safeguarding national defense, shielding spy protocols, and keeping foes in the dark about our monitoring reach. Yet this veil of confidentiality breeds doubts about other concealed matters. If certain aerial scans get locked down for security purposes, could others be sealed for alternative motives? If authorities uncovered signs of alien tech, would they go public or bury it? The mechanisms for classification are in place. The track record of holding back space intel is established. Linking these threads, justly or otherwise, sparks ideas of orchestrated silence. Comparable dynamics emerge elsewhere. When the Department of Defense unveiled UAP footage in 2020, verifying that fighter pilots had spotted sky events resistant to simple rationales, it backed assertions long pushed by UFO investigators. Officials were indeed monitoring baffling flying entities. They did possess unreleased recordings. In that instance, those warning of incomplete disclosures turned out to be spot on. This hardly proves all such theories hold water. Most don't. Still, it damages the standing of bodies that once ridiculed subjects as absurd, only to later confess they've been studying them seriously for years. The abrupt reversal shakes reliability. If past statements were off-base or evasive, what grounds us to trust current ones? The 3I Atlas episode unfolds amid this tangled terrain of credibility, openness, and conjecture. It could simply be a comet. The oddities might stem from partial data and fade with fuller evidence. The withheld NASA shots may surface someday, revealing mundane terrain. Or perhaps odder developments are afoot, whether in the entity itself or the oversight of its details. Lacking complete access, everyday people can't assess these matters on their own, relying on official filters for data drops, background, and interpretations. When those entities clam up during pivotal times, speculation rushes to fill the gap. Part of it makes sense, probing valid concerns over skin schedules and info access. Part veers into the extreme, tying 3i Atlas to baseless tales of covert cosmic ventures and otherworldly encounters. For researchers embedded in these systems, openness has boundaries. Certain datasets demand precise adjustments prior to sharing, since unprocessed views can deceive. Some intel is bound by global pacts on orbital tools. Some outcomes require expert vetting before airing to sidestep hasty judgments. These are all valid grounds for holding back immediate full disclosure. But to observers outside, they come across as dodges. When buzz surges over a find, when curiosity hits its zenith, when all crave updates, demands to pause for weeks of refinement feel like obstruction. Legitimate procedural hurdles don't alter the gut reaction. This friction won't vanish with 3i Atlas by itself. It's ingrained in the setup of contemporary research, nested in organizational setups with their agendas, limits, and caution levels. Experts prize meticulous checks. Audiences crave instant candor. Online platforms favor haste over precision. State entities favor oversight to revelation. These rival priorities collide time and again as contentious issues surface. What 3i Atlas signifies, apart from its traits as an interstellar. This interstellar visitor serves as a prime example of navigating peculiar discoveries amid widespread information, sharing, and waning faith in institutions. The old paradigm, where specialists issue declarations and the populace takes them at face value, has crumbled. Folks now demand proof beyond mere outcomes. They seek the raw figures, conduct their own examinations, and draw personal conclusions. Hobbyists in astronomy, pulling NASA's unprocessed photo collections and crunching them on their own, illustrate this transformation. They refuse to linger for sanctioned announcements. They decline to blindly rely on authorities to disclose all key details. Instead, they seize accessible records and pull out insights independently. At times, their efforts spot oversights from formal pipelines. Other times, they err in ways that refined tuning could prevent. Yet, the drive to confirm over-comply mirrors wider societal evolutions regarding power structures and specialist knowledge. The scientific world has evolved with earlier societal turns. As the printing press broadened knowledge dissemination, as widespread schooling boosted reading skills, as higher education welcomed students from non-elite backgrounds, researchers refined their outreach strategies. Today's pivot to online platforms and decentralized data flows calls for parallel adjustments. Experts must devise ways to uphold precision and truthfulness in arenas that prioritize quickness and interaction. Oumuamua will ultimately exit our solar realm. Come late 2026 or early 2027, it will surpass Neptune's path and venture anew into the void between stars. Monitoring will cease. The body will recede into obscurity, beyond the reach and brightness detectable by our instruments. Any insights we gain about it must come prior to its vanishing act. Thereafter, it joins the catalog of records, a benchmark for upcoming scholars probing crowds of extrasolar wanderers. Still, the inquiries sparked by Oumuamua endure. Probes into assessing odd sightings. Debates on what proofs warrant outlandish theories. Issues of organizational openness and citizen data rights. Reflections on science's role in today's data-saturated world. These go beyond scholarly musings. They shape collective choices on matters ranging from cosmic mission focuses to grant allocations to public STEM training. Should Oumuamua prove merely a comet, its role remains worthwhile regardless. It compelled these dialogues. It exposed flaws in our sighting tools, shortcomings in data-sharing protocols, hurdles in conveying ambiguities to lay viewers. Such takeaways extend far past this single anomaly. And should Oumuamua reveal itself as exceeding a comet, say, through December sightings or JUICE mission findings uncovering unnatural traits, then these talks gain heightened urgency. Society's reaction to verified signs of alien tech will hinge in part on bonds of confidence between bodies like agencies and everyday citizens. With perceived candor from officials, reactions can proceed orderly and measured. Amid suspicions of secrecy and suppression, they devolve into turmoil and division. We're nearing the juncture where these dynamics face real trials. Perihelion lies in the past or present as you hear this. The intruder lingers sunward, pursuing its unseen activities. Before long, it reappears. Scopes will train on it. Photos will pile up. Streams of info will pour in. Solutions, or at minimum tighter-framed puzzles, will emerge. No matter the outcome, Oumuamua has secured its astronomical legacy. The third extrasolar guest to arrive precisely when our spotting tech had ripened to detect it. Odd enough to ignite rigorous expert discourse, enigmatic enough to seize collective curiosity. It journeyed from stellar abysses, bearing riddles we're only starting to articulate, much less resolve. In mere weeks or months, we'll discern if those riddles yield simple replies or veer into unforeseen territory. Terrain that reshapes our grasp of our spot in this expansive stellar district we're just commencing to chart. The anticipation lingers. The watch begins. Oumuamua's tale develops dusk by dusk via scopes dotting our modest world. We all observe in unison as this timeless rover traverses our fleeting abode. This fleeting crossroads of paths amid the stellar gloom.